Hello and welcome back to the Inside Java podcast, the podcast about everything Java, brought to you by the team at Oracle that builds Java. My name is Nicolai Parlog, and this episode of Ask the Architects is a conversation with Joe Darcy, lead of OpenJDK's compatibility and specification review group and, important for our conversation, committer to Project Valhalla. As part of that work, Joe is expanding Java support for custom numerical types, which goes beyond value types. Side note, the value types preview was merged into the JDK's mainline and is available in the JDK 28's current early access builds. But numerical types also need operations, and while Java is extremely unlikely to ever allow arbitrary operator definitions, it may well support limited operator overloading. So your value types could be added or multiplied with plus or multiplication signs instead of annoying method calls. The mechanism that's supposed to deliver that feature set is known as type classes, which is what Joe and I spent most of the conversation on. We also touch a bit on a few algebraic topics and floating point imprecisions, so this is a more geeky Inside Java podcast. An even more geeky Inside Java podcast. Enjoy the episode. Joe, here at JavaOne, you gave a presentation about numerical types and what Java, how Java is supporting them at the moment, and what Java could potentially do in the future there. So let's start in the present. What does it mean for Java to support a number? Or maybe even, and I saw your presentation, spent quite a lot of time there. What even is a number?
Well, mathematicians have been working on that for a few thousand years. So there's a lot of prior art they have, or a lot of explorations they've already done. I think more casually, we might think of a number as something we can add, subtract, multiply, and divide. And for types we already have in the platform, we can do that with primitive types like int, float, and long, and double. We can also do it with types like big integer and big decimal. So we're looking to expand the set of numbers we can use in the platform for a variety of purposes, including small types for AI purposes, as well as additional larger types for other kinds of numerics and computations.
Mm-hmm. And so when you already made a distinction there between primitives and then big decimal and big integer, the obvious one is that big decimal big integer is a reference type. My understanding is that there's nothing special, or maybe there's some intrinsics or maybe some other optimization, but technically speaking, I could have implemented that type, right? In a user space, there's nothing special about that.
Fundamentally, types like big integer and big decimal are in user space as reference types. Depending on the VM version, they may or may not have intrinsics, or especially big integer to speed things up. As we know, for Project Valhalla, one of the main goals of Valhalla is to bridge the divide between the capabilities of primitive types and reference types, so we can have the best of both worlds. And we're looking to take advantage of those features with value classes in particular to write new numeric types in the platform, as well as allowed library developers to write their own numeric types, so they can get a lot of the capabilities of primitive types, but they can define their own.
Yeah,
which we can't do today. So.
Yeah, exactly. So let's set the stage a bit. What does it mean for Java? What does int? What are all the things that make int special?
Primitive types in Java have a number of capabilities that a reference type don't have. You have literals for them. You have operators. You have compiler-supported conversions between the primitives. Say when you're calling a method, and there's constant folding. Mm-hmm. And we don't have those for reference types. For type classes, we're looking to provide initially support for operators and for conversions. And those other capabilities we're leaving to future work once we get those first two worked on.
Okay, specifically the one with operators is interesting, right? So you have, that's also a big divide between int, for example, and integer or big integer,
yes.
Which nobody enjoys. I mean, like it is what it is, but nobody enjoys writing out dot plus,
yes.
like not the character, but like the method name.
Yes, yes. If it's dot add or subtract, it takes more characters, but it also makes the source code less portable. Like if you have to translate code to go from int or long to big integer, you or your IDE or other tooling has to rewrite it.
Yeah.
Or you can't just transliterate a formula out of a textbook into your program because it's using the wrong notation.
Yeah.
or not notation. So that's part of the capabilities we want to address using both value classes and another feature that's in development in Valhalla called type classes. Type classes are a technique originally developed for the Haskell language to allow kind of disciplined operator overloading. So the way we're looking to adopt it in Java is to have an interface with some name, say JavaOne numerical, that would declare that, a class that had a witness for that interface could opt into using operators. So if the compiler saw that your class, like say unsigned int, had a witness for this interface, then the compiler would know you could use operators on that class that you defined.
Yeah, that's like a much more narrow way to allow operator overloading than a wider sense. What some languages do is like, well, if you define a method called plus, then we'll just translate that to the operation plus. But that means
right.
I can make every class of mine plusable, so to speak. I can give this to everything, which, at least it's questionable whether that is something that I should be able to give to arbitrary classes, because it gives developers the tools to play code golf, to be like, I want a plus, I don't know, maybe 2 users, and then the combination is whatever that would be. And I do that a bunch. So instead of combining 2 users with like a meaningful method name, I'm just going to call it plus, and then I can write it out.
Right.
And I think specifically if you can, even wider is the option to just define the actual operators, and then you can just do whatever you want. That's even wilder than like I think that is clearly failed. I think in language design space, where people can just like create arbitrary sequences of characters as an operator.
Well, it's easy to misuse or use in ways that many people would term unfortunate. So we want to help guide the usage of the feature by clearly indicating these operators are meant to be used as groups together for number or number-like types.
Yeah.
And different kinds of numbers would have different operators available to them. So we see in the Java platform, for example, the integer types like ints and longs have many more operators than, say, float or double, like all the shifting operators and bitwise operators. So the feature, as we're designing it currently, there are ways to indicate this is a integer-like type, so it has access to those other operators appropriate for integers.
Okay, so that means that is the part of the idea here that the existing primitives could theoretically be mapped back to type classes. So let's say Java is redeveloped to the current point and type classes are already in. Would then the goal be that int has nothing special? It would really just all the int capabilities would flow from type classes?
If we ever get there, I don't think that would be in the first iteration. So certainly Brian Getz has talked about a future where a lot of the special specification in the Java language specification to deal with ints and longs as primitives would be migrated to libraries and could be re-implemented using value classes. So we would be able to implement equivalent functionality to ints and longs with the new feature set, but we wouldn't necessarily have to re-implement what we already have in the new features.
Yeah, I'm not proposing to actually re-implement. I'm just wondering whether this system will be powerful enough to theoretically have all of ints, for example, longs capability flow from that.
That would be the intention.
Yeah.
And in terms of a platform design, the virtual machine specification has a lot of special support for a subset of the primitives. So the way you'd want to compile down, so even hypothetically, if we had type classes to support 32-bit int as we have in the platform today, you would still want it to compile down into the VM instructions that handled int specifically. Which you wouldn't necessarily expect or get from other types that didn't already have that built-in VM support.
Yeah, that makes sense. You just mentioned, or you earlier mentioned the term group. You did not just say that as a bundle of operation. You meant something very specific with that, right?
Well, we do have to be careful with terminology in this space because there are mathematical meanings to the terms group ring and field in terms of abstract algebra that describe if you have a set of elements and operations on those sets of elements, if the operators have certain properties, you say that's a group, a ring, or a field, and those are kind of have more properties as you go down that list. So the usual arithmetic properties we're used to in terms of simplifying expressions, that you can change the order of the operands of a multiply, for instance. So we would say that multiplication is commutative, same with addition, or multiplication distributes over addition. You know, A times, in parentheses, B plus C is the same as AB plus AC. So all those properties we're used to are due to the field axioms, because real numbers are a field. And so we're used to those sort of transformations being allowed. And there's a very rich mathematical studies behind all those kinds of structures and what they mean. So we're looking to be informed by those kinds of structures when we design the new features for Java numerics, but we don't intend to replicate or represent all the richness that's been developed by our mathematician friends over the centuries for our APIs.
Yeah, that makes sense. But it would also mean that when I use a plus, and I mean like in the hypothetical future where type classes landed, when I use a plus, then my intuition about how plus works, you mentioned commutative, or the fact that it doesn't matter which order I resolve a series of pluses, right, the result will always be the same, that those intuitions, like Java would force me into making my plus follow those same rules, right?
So this is an interesting question about what exactly does a plus or times mean? Yeah. And what, because one of the reasons we looked at different kinds of numbers is because different kinds of numbers have different properties for their operators. So for example, something we're used to from multiplying integers or real numbers is this commutativity property we mentioned, like A times B and B times A are the same. That doesn't hold true with matrices.
Yes.
All right, so we know, like, if we have a 1 by n matrix and we multiply it by another 1 by n matrix, we'll either get an n by n matrix or a 1 by 1 matrix, depending on which order we do them in. And this is very surprising to students who run into it for the first time when they start studying linear algebra, and it was surprising to physicists when they started using it for quantum mechanics because it was unfamiliar to them. So we don't want to constrain the solutions we have for the language features to assume that, well, everything you might want to multiply together, it has to be commutative, because we know there are numbers or number-like objects people want to operate on, like matrices, that don't have all these properties.
Yeah, and that ignores the fact that if floating point numbers, actually all of those intuitions are already wrong.
Right. Well, as you know, I do work in floating point, so I've mentioned in some other context from an old social media poll I did that floating point was both more feared and more loathed than spiders. So it's not popular. One of the reasons it's not popular is because essentially all those arithmetic properties you're accustomed to with real numbers don't hold when you're operating on floating point numbers. So you're very constrained with what you can do if you want to exactly preserve a certain kind of semantics.
Yeah, so to explain that to the audience, like, of course, if you multiply 1.0 by 2.0 or the other way around, you both times get the same result. But the problem is then if you go into numbers, which is because integers within their range cover all the numbers in the range, floats cannot do that. So they are full of holes, right? And those holes are infinitely large. And so, like, when results fall into these holes, we get rounding, and then the sequence of operations matters a lot.
Yes. So floating point is fundamentally discrete. So that's a big difference from the real numbers that are continuous. So one of the convenient facts of real arithmetic when you're working in that area is that between any two real numbers, you can find another one. You can just take their average, for instance. So that's not true for floating point numbers. At some point, you have one floating point number, and then you have the next larger floating point number, and there's nothing in between in that numerical range.
Yeah.
So and that's actually ties into how we evaluate the accuracy of a floating point method. So the distance between those representable floating point numbers is called an ULP. And we say that a floating point method is correctly rounded if you always get the floating point number closest to the exact mathematical result.
Yeah.
Can't always do that. The floating point arithmetic operations work that way. Usually we have a somewhat looser standard for the Java-like math methods where they can return one of the bracketing numbers of the true result or one a little bit further away.
Is that the difference between regular floating point math and like strict FP? Is that what the strict is, or is that something else?
That's something else. That was it's a long, complicated story behind that. The main takeaway is we don't have to worry about strict FP anymore since we added essentially we added strict FP-ness back to the platform all the time as of a JEP number I have to look up a number of releases ago.
Okay.
If you're interested in learning more about strict FP, I gave a talk at the JVM Languages Summit a number of years ago that discusses why retiring strict FP would be a good idea.
Yeah. So, okay, I'll put that in the show notes for people to follow up on. Yeah. So let's talk a little bit maybe about the mechanics of type classes. I understand that syntax is totally up for grabs and it's way too soon to even think about that because all of this is very exploratory still. But so not based on syntax, but based on like on the mechanics. So say I create my own. Let's take big integer for example, and I want to now make it so you probably in the future want to make it so that big integer works with like the plus character operation as opposed to plus the method call. What would big integer have to do to make that happen?
Big integer specifically probably couldn't play in this space under the current design. The current designs from Valhalla is that to use operators, you'll have to be a value class. Mm-hmm. Unfortunately, big integer, when it was added to the platform, wasn't final and it is subclassable. So we would need so we recognize this is an issue.
Java's wrong default, striking again.
Well, but we would want to have some way to get arbitrary precision integral values under this regime, even if it's not through big integer. So if we have to introduce some large integral or some other way to get this functionality.
Okay, so step one is be a value, which makes perfect sense. And as you said, like also string wants to be a value just by spiritually it wants to be a value, but again also for similar reason it's just not going to play out to be one. So step one, be a value. That makes a lot of sense, which means it doesn't have identity, that the VM is free to replace instances with a value, scalarize them, and all that stuff that we are waiting for in Valhalla and which is described in JEP 401. And that makes sense that to limit math or arithmetic, maybe I should say, to those types. Okay, so I create my own new big integral type. Right. That's what I'm going to call it, and I'm going to make it a value. Mm-hmm. And then what would be the likely next steps?
So there'd be a few things you would have to do as the library author. So you would have to implement the operations you want. So add, subtract, multiply, divide. If you wanted to offer integer-specific operations like the shifting and bitwise operations, you'd implement those too.
And I implement those are like, okay, wait. So you just mean like methods, right? That's when you say
just as static methods on the class.
Static methods on the class, okay.
Then there would be a declaration of a witness. This would be the idiom that tells Java-C that your class is opting into providing operator support. Yeah. And that witness would be a field that would point to an object that would do the mapping between the designated method that gets called for, say, the plus operator and the method or logic on your class that implements the addition operation.
So I know that, again, I want to highlight that. This is not about syntax, but I'm thinking now immediately when you say that, it sounds like kind of like an interface, basically like a glue interface, like an adapter maybe that says, okay, I know that plus needs to do this, and I know this method, this class has the capability to be plussable, right. And I'm just gonna, as you said, map between those operations. Yeah.
Right. So the notion of the witness interface is that the implementation of that interface does the mapping between the recognized method that implements the addition operation and the logic in your class that provides that functionality. Okay. So in the prototypes, we have the implementation of the witness objects is very straightforward. Like an instance method called add in turn calls a static method calls add on the two arguments, you know, and so forth for all the other operations. So it's very. Why
is there this indirection through this type class and witness structure at all? Because the way you describe it, I could think, but wait, couldn't you just give me an interface that my big integral type just implements? You just call it plussable and it has a plus method, and I just implement the plus method.
There are certainly many potential ways that this could be done. Some of the advantages to using type classes is that it's a mechanism that also allows other functionality related to this, such as conversions.
Okay.
So we want to, one of the capabilities primitive types have is that there are automatic conversions built between them for method calling. So if you have a new numeric type, say your large integral type, and you wanted to interoperate with the existing types, you want to get the effect of being able to add an int or long to your type. Mm-hmm. So you could certainly have explicit factory methods or constructors that did the conversion for you. It would be more convenient if there was some automatic conversion. We didn't have to see the code.
Yeah.
So potentially one way that could be done would be to have lots of overloads of an add method. There's an add method where, you know, the left operand is a large integral, and the right operand is an int. And then the left operand is a large integral, and then
you going with this, it already sounds terrible.
All right, and then you do the other ones, and then there have to be rules about how. So instead of that, the guidance we're getting from Brian Getz is to look into conversions where witnesses could be used to guide automatic conversions. Say if there was a lossless conversion from int to this new large integral type or from long, then that could occur. And then the operators themselves would be constrained to have a homogeneous typing, meaning you'd have like foo, op, foo, yields of foo, as opposed to having the types of the two operands be different.
Okay.
And so that's how the conversions would work together with the operators as a joint design. Mm-hmm. So we'd be getting the ability to mix operands by allowing the compiler to help out with doing automatic conversions.
Okay, so that's the way you describe it. It's quite a lot, right? It's quite a lot of new language and VM machinery. Also, when I think about like learning that, right? That is not something that is necessarily, at least the way that it sounds not very familiar to developers, and familiarity it's not that essential. But I'm just saying, I'm assuming that it's like you're still exploring this space, or like where would you put that on the map?
We're still exploring this space. I think a few benefits of this approach is that for end users who are using the numeric types, it should be very easy to use. You would just use the operators that you're accustomed to from the primitive types, and they would just all work and more or less do what you want, depending on the semantics of the class in question. For the author of the numeric type, it isn't too much additional work to provide the witness declaration and then the implementation of the interface, because you're already providing that functionality. It's just registering a way that the plus operator should map to this method indirected through an interface. Yeah. One advantage to the prototype approach we're using is that it uses the invoke dynamic feature in the VM, so that the code idioms are emitted in ways that are very amenable to hotspot and other VMs, making them go fast. Mm-hmm. So even if there's some indirection in the class file or at compile time and how JavaC compiles the code, at runtime, once the optimizers kick in, it should run very quickly.
Yeah, because in the end, it will still mostly boil down, I guess, to today's primitives, right? When I would write my big integral or whatever else, if I would have complex number, then in the end, they would sooner or later probably contain ints or longs or doubles or floats, right? Because that's just the basic building blocks, I say, how to put numbers together. That's correct? Is that a correct assumption? That probably most things will end up being wrappers around primitives?
I would expect many of the numeric types would bottom out at, ints, longs, floats, or doubles at some point, but you could potentially use it for other kinds of numbers that wouldn't have that interaction. But I would think that would be the most common case.
Okay, and then in the end, it boils down to the VM instructions for these primitives, and then if the just-in-time compiler can strip everything else away, as you said, like through a help or something like invoke dynamic, then we're getting primitive performance, hopefully, or ideally, or close enough at least. So it's not like a huge performance gap like you have with like dot plus on some of these methods.
Right. I think the overhead of going through an operator would be very small to negligible once the VM warmed up.
Yeah. One thing I'm still wondering is, ideally, we want, if you have something like plus and minus, we want those to be inverse. What's it called? What's the term? The mathematical term that I'm drawing a blank on.
Yes, additive inverse would be the one. Yes.
Yeah.
Yes.
Ideally, we want, like for from the perspective of a user of a class, I would want the plus and the minus to do the opposite thing. And I guess that from the design perspective of the language, you'd want that also to be the case, so users like me don't get confused. Is there any way that the language can do more there than, plead in the documentation to please do that?
So we're for future work, after we get this first set of functionality in, we have had a few initial thoughts about, would there be a way to allow a numeric type to declare, I actually do follow those properties of a group, a ring, or a field, and maybe that would allow some future runtime or backend to take advantage of those additional properties. So something like a marker interface that we would have to say these implementations had extra semantics, but that's pretty far off if we get there. So.
Okay, but that would still just mean as a user would have to do it right and then mark it accordingly. There's no way, I guess, for the runtime to find out or to confirm somehow whether I did it right or to even enforce it, right?
I think that would be difficult. That's we kind of veer into like proving programs correct at some level. So there are cases where it could be done, but I think it's a hard problem to do in general. Okay,
but is my understanding of type classes correct that it wants, like, it's not like there's one type class, there isn't anything at all. But the idea is not to have one type class for plus and the other for minus and the other for multiplication. It's more like they come together, right? It's like, you want to do both of those at the same time.
Right. The groupings we're using would be that there'd be one type class for all the arithmetic operators. So plus, minus, times, divide, negate. Those would come as a bundle. There'd be a separate bundle for the ordered comparison operators, less than equal, greater than equal, and so on. And then your type would have to declare like which bundles of operators it supported, but you couldn't say I support divide and greater than, and that's it. You'd have to support all of them. That would be the expectation. So.
Yeah, that makes sense. I think like that at least makes it. I mean, as a developer, you can often do as you please without anybody being able to stop you. But assuming at least you work like in a team where people look at your code, then implementing half of those methods and throwing unsupported operations exceptions from the other one is probably going to raise some red flags in my code review.
That would be frowned on. You'd hope that would be caught in code review. And one of the API design questions is how many of those methods should be allowed to throw unsupported operation exceptions. So it's pretty common to not support divide on all operands. So, for example, it's common to throw an arithmetic exception on divide by 0. Yeah. So we would certainly want to allow that. And there are many other kinds of numbers where divide isn't really well defined. So you'd want to have some kind of exception be allowable and expected if documented in those kind of cases.
Yeah, that makes sense. Like I think the challenge there is to do it in a way that the contract doesn't get, like that the contract is not too restrictive, but at the same time doesn't just allow whatever, because like for every rule there's one exception, so there's going to be no rules. So I can assume that it might be hard to find like a good space there.
This also points to a classic design constraint between lumpers and splitters. So this term comes from our friends in biology who would have heated discussions about, does this group of animals deserve to be its own species or not, or should it be grouped in with some other group of animals?
Yeah.
So there are big, long discussions about them. But we have similar things in computer science and API design. So one small issue that has come up for the numerical API design is the negate method, because we want to have unsigned integers, for instance. So what does it mean to negate an unsigned integer? Well, there are a few things it might mean. It might mean subtract from 0, which is how the JLS defines it for certain types. You might say, well, it should just always throw an exception because it's undefined for an unsigned type. That would be reasonable as well. So the splitter solution would be there should be a separate unsigned integral interface that's distinct from the interface for signed numbers, so that way you don't have to define negate. But in that design, you have this entire other interface to keep out design for the platform and specify and handle, as opposed to, say, just having the negate method throw unsigned operation exception in some cases.
Yeah. That sounds eerily familiar of how the collections framework works, right? Where you have the same discussion about, I mean, that should I say it now, but would it have been better to have not only collection, but a collection that I cannot mutate? Somebody else could though, but I'm having only the read methods on it, is what I'm meaning. And another one that has the mutating methods on it, for example. And that would be the splitter, or the more split version, because you could split that further. The one argument against the splitting is, well, actually, if you look at a problem long enough, you can split it down further and further until you end up with atomized and borderline useless type hierarchy. And what you call the other ones, the splitters and the
lumpers.
The lumpers, yeah. And maybe the collection framework is more a little bit on the lumpy end, where it's like, no, we have like all the methods in collection, they all make sense. It's just like half of them might not do what you think they want to do.
Perhaps we'll draw some inspiration from collections and include a short design document for numerics when we put them in the platform in the future.
Collections is actually interesting because I know that in some languages people are like, well, you can plus lists, you can minus lists. That's reasonable. But that would not work in Java because lists cannot be... Wait, I'm stopping myself. Can lists not be values? I could write a value wrapper around a list, right? I could write a value class that, as a single reference field, holds a list. And then there we go. I'm already breaking the design I'm feeling. I'm already worried that I get into trouble here.
Yeah. Well, this is... there are simpler... kinds of algebraic structures like monoids that would just have a plus operator, but we're not looking to include those at the moment as part of this effort.
What about neutral elements? Is that something that the language needs to know about? Like, does it need to know that this type has a 0 that with this operation does nothing, like a plus 0 does nothing, a times 1 does nothing? I know that because I did study math a bit. I actually have a little bit of a background there in German, unfortunately. So some of them, and also a long time ago, and mostly unused since then. So I cannot map all the terminology that you're using, but I have like a sort of rough outline in my head. And I know that back then, those neutral elements for the algebraic exploration of this was super important.
Right.
Are they also important for Java to know? Does Java need to know that there's a 0 that does nothing for addition, for example?
With the current design that we're looking at, you could look at the semantics of the interfaces we're defining as if a class has a witness for this interface, it can use this set of operators. That's the current design. If in the future we follow some version of additional marker interfaces opting into constraints on the semantics of the operators, in that case, you would probably also want to add a few new methods, so they wouldn't quite be marker interfaces, that would add what is the multiplicative identity versus the additive identity, because those would be a very core part of being a group ring or field would would be being able to identify those identity elements.
Okay. Not sure whether that applies there, but one thing where something similar pops up is in like a streams reduce, right? Where you need to provide a starting element,
Right.
and that starting element better be a neutral element of the operation, because otherwise, if a parallel stream splits this up, so for example, you reduce a stream and you do something additive, and you take as the initial element 1, and then this ends up being done in 5 threads.
Right.
You now have the 1 5 times, and that's probably going to not give you the result that you want. But I'm not sure whether, because that's a situation where it would be kind of nice if somehow magically the reduce operation would see, oh, you're doing this with an int. You don't need to give me the 0. I already know 0 is the answer.
Right. You happen to know for the primitive types what the identity elements are, like 0 for addition and 1 for multiplication, and likewise for floating point. That's as close as you can get. But you wouldn't know for user-defined types what those would be. So you would need some method associated with the numeric type to provide those values for you.
Okay.
To do those kind of reductions. Yes.
So we said already a bunch of times that you're still exploring all this. I think it's kind of challenging to talk about this because I know from Brian's keynote yesterday, he mentioned very explicitly, it would be really good to spend more time talking about the problem. And I noticed during our conversation, due to the questions that I asked, I think I mostly failed at that, right? Because we talked a lot about the one solution, not the one solution, but like a complex of coherently fitting together solutions that's currently swirling around, that it could in the end maybe be what gets proposed. Although that at this point, as I said, is kind of vague. Do you think there's something noteworthy maybe that we can discuss in that problem space that maybe you don't have a solution for yet, or that maybe shows how different solutions could fit together? Because you also sometimes said, it could be done like this, or maybe in the future we can look into that. So to maybe drag the discussion of this, not necessarily only ours, but also when the wider community watches or listens to this, to think about this in a way that is more productive than, because at this point it's not productive to say like, oh well, they said this is what this will be a marker interface, and that will be a type class, and this is how you define a witness, because nobody knows at this point.
In terms of talking about the problem or the programming capabilities we want to add to the platform, we can say that different kinds of numbers are a very important part of programming, and computer science and mathematics, and we want to let the Java platform have better support for this kind of numeric programming. This is important to continue broadening the platform support and usability, so we want it to be better for things like traditional scientific and engineering computation, and over the years there have been groups that have encouraged us to do that. Of course, students use various kinds of numbers in their studies, so having better numeric support could help with paving the on-ramp sort of activities to bring the next generation of Java developers on board. And in the AI and machine learning space, they tend to benefit from using smaller numeric types than we have currently in the platform. So that's another reason we want to expand the ability of the platform to support whatever new numeric types are useful in how Java is being used today and how we want Java to be used tomorrow. So that's the basic problem we're trying to solve.
Yeah, I think as one other fact of the way that the Java and the JVM work right now that precludes a whole host of things you could possibly do is bytecodes are limited. Also, nobody's really looking forward to creating like 6 extra primitives, which get like, I know that there's this conversion table in the JLS, which would just explode that one with like 6 more rows and columns. So part of the problem is also that the route that Java took in the past with those explicit primitives is not something it wants to continue going down, and also arguably can't, even if it wanted to, without like serious hurdles, like for example, bytecodes running out.
Right. So in rough terms, there are 256 possible bytecodes, of which 200 are already allocated, approximately 200, and float and double each take about 20 bytecodes. So rough. There's not a lot of space left if we were to do things the same way.
So half float would eat half of your remaining budget.
We would probably be able to do it with many fewer, but we want to have the ability to add many more types, including user-defined types. So we don't have enough opcode space. So to follow this path, we need some other solution, and that's where Project Valhalla and type classes are we're looking to use as the enabler to have these capabilities in the platform.
Yeah. Okay. So what would be the timeline? I don't want to talk about timeline, but I want to talk about roughly like an order of, it's like a sequence of events maybe. So I guess since you are doing this under Valhalla, and I guess Valhalla is kind of busy with the whole value type situation right now, do you, from an organizational perspective, it probably makes sense to get value types much further than they are now. But are there also like dependencies, just depends on the things that you need in the VM before this could even land? So for example, values need to be in there, something else?
Right, we would certainly need values. We currently have a separate type classes branch in the Valhalla repo where we're hosting this work. So we have a number of prototypes of numeric types already there that we're experimenting with. So the type classes mechanism currently supports operators. So we're enjoying some operator-based programming on these new numeric types. And next, we plan to look at conversions between these different numeric types as the next major piece of functionality to take on.
Okay, good. Joe, do we have anything that you feel we left uncovered? Something we should touch on before I let you go?
I think that's it. I'm really looking forward to having more numeric types in the platform. It's been something I've been interested in for many years, and I'm happy to be able to be working on it again.
Yeah, thanks for taking time and for being here, and for all that good work. And go do it quickly. Everybody, all right. People are eagerly looking forward to this.
The team will do our best. Okay,
yeah.
thanks,
Thank
Nicolai.